Hello everyone, welcome to this lecture on combinational logic circuits. In the previous lectures we have discussed in detail about the logic gates and the introduction to digital. And in today's lecture we will discuss in detail about the formation of these logic circuits using the logic gates. So the logic circuit formation is divided into two parts. One is combinational logic circuits, another one is sequential logic circuits. So all these logic circuits are built using logic gates, but there is a difference between the conception of combinational logic circuits and sequential logic circuits. These combinational logic circuits are memoryless digital logic circuits whose output at any instant in time depends only on the combination of its input. That is, the output present only on depends only on the present input. So here we can see the representation of the combinational logic circuits at the bottom. It has three inputs, namely capital A, capital B, capital C. It can be extended up to n inputs. So starting from single input, it can accept up to n inputs. The outputs also can vary from 1 to n. So here the outputs are represented as capital Y and capital X. So the output is the function of input. That is a basic representation of a combinational logic circuit. These combinational logic circuits are classified into many categories based on the functions, based on the arithmetic and logical functions, based on the data transmission, based on the code converters. Based on the arithmetical and logical functions, the circuits are divided into adders, subtractors, comparators, PLDs. PLD means programmable logical devices. And based on the data transmission, it is divided into multiplexers, demultiplexers, encoders and decoders. And finally, based on code converters, it is divided into binary, BCD, binary coded decimal and 7-segment circuits. So we will be discussing each and every type in detail. So to start with basic circuit, which is arithmetic and logical function. Half adder is the basic thing that we should know, the circuit implemented using the logic gate. So it is a general arithmetic operation. So normally for adder operation we require minimum of 2 input. So in general addition operation we will be having one output. That output one will be taking it as sum and another one will be taking it as carry. So similar to that in digital arithmetic also we will be using a minimum of 2 input and 2 output. So the 2 inputs are capital A, capital B, and the 2 outputs are sum is represented as capital S and carry or carry out, which is represented as C. If carry out means we can also represent as C suffix out. Out means output. And when the inputs are, number of inputs are 2, we will be naming the circuit as half adder. When the number of inputs are increased up to one level higher, that is, if the number of inputs are 3, the circuit is named as full adder. So here we can see the half adder combinational logic circuits with 2 inputs and 2 outputs. So basically based on this truth table logic and by continuing with the KMF, we will be building this logical circuits. Here it is given directly. So for half adder, the sum is expressed as the XOR of 2 inputs and the carry is expressed as the AND of 2 inputs. So based on that logic, here the logic implementation is given. So sum capital S is equal to A, capital A XOR B, capital B, and the carry capital C is equal to capital A and capital B. So based on this logic expression, we can form the logic output. So for the 2 inputs, we all know the input combinations are 0, 0, 0, 1, 1, 0, 1, 1. So for using this sum and carry logic, so we can fill the truth table output as for 0, 0 the sum is 0, for 0, 1 the sum is 1, for 1, 0 the sum is 1, for 1, 1 the sum is 0. That is based on the XOR logic. And we will fill the carry logic based on the AND logic. The carry for 0, 0 the carry is 0, for 0, 1 the carry is 0, for 1, 0 the carry is 0, for 1, 1 carry is 1. So it is a basic building block for addition of 2 single bit numbers. So this circuit has only 2 outputs, namely carry and sum. Next we will discuss the full adder. So as I already said, here we have one more input, that is carry in, C suffix in, and we have C suffix O, that is carry out. Here the carry is represented as 2 forms, one is input carry and another one is output carry. So similar to half adder, the sum is expressed as the XOR of the three inputs, and the carry is expressed as the AB, that is A and B, or with A and C in, or with and B and C in. So based on this logic, the logic circuit is given, and this full adder is developed to overcome the drawback of half adder circuit. You can add two 1-bit numbers capital A, capital B, and a carry C. The full adder is the 3 input and 2 output combinational circuit. So based on this logic, we can construct the truth table as shown in the slide. So for the inputs, for the 3 inputs, we'll be having the input starting from 0, 0, 0 to 1, 1, 1, 1. So 0, 0, 0 means weightage is equal to 0. So the range of the input combinations is from 0 to 7. For the 0 to 7, we have found the digital input from 0 to 0, 0, 0 to 1, 1, 1. For 0, 0, 0, the sum is 0. That is based on the XOR operation. For 0, 0, 1, the sum is 1. For 0, 1, 0, the sum is 1. For 0, 1, 1, the sum is 0. For 1, 0, 0, the sum is 1. For 1, 0, 1, the sum is 0. For 1, 1, 0, the sum is 0. For 1, 1, 1, the sum is 1. Similarly, for carry, based on that logic given, CO is equal to A and B, or A and Cn, or B and Cn. So the CO is for 0, 0, 0, the carry out is 0. For 0, 0, 1, the carry out is 0. For 0, 1, 0, the carry out is 0. For 0, 1, 1, the carry out is 1. For 1, 0, 0, the carry out is 0. For 1, 0, 1, the carry out is 1. For 1, 1, 0, the carry out is 1. For 1, 1, 1, the carry out is 1. So that's all about full adder. So based on this full adder, we can construct the 4-bit parallel adder. That is, we can increase the number of bits given to the A and B. So far we have given only single input, that single bit as input. So we can extend this bits from 0 to n. So here we can see the 4-bit representation. So for 4-bit representation, we need to use 4 blocks. So if we start from LSPs, that is from right hand side, full adder 0. For full adder 0, will be having A0, B0, C in as input, and S0, C0 as output. Then for the next preceding one, next preceding value, full adder 1, A1, B1, C in as input, and S1, C out as output. Similarly, for full adder 2, A2, B2, C in as input, S2 and C O as output. For full adder 3, A3, B3, C in as input, and S3, C out as output. So this full adder is capable of adding only 2 single digit binary number along with the carry input, but in practical we need to add binary numbers which are much longer than just 1 bit. For this purpose, we will use this 4-bit parallel adder. So we'll discuss about the subtractor concepts in the next lecture. So I hope now you understand the basic introduction about how the logic circuits are built using logic gates. In that we have discussed about the construction of a half adder and full adder and its application as 4-bit parallel adder. Thank you for watching this lecture.